yeah, basically, if I'm sharing, I can like do a quick intro of GDS Factory for those of you who are new. But yeah, the goal of GDS Factory is to make a software that can do all the tasks for chip design. So it's all-in-one solution for chip design. The software came from Photonics, Quantum, and MEMS because these basically new fields, they don't really have good tools. So we made GDS Factory almost, yeah, it's like 6 years ago. So I work in transceivers in Intel and HP, and then I went to Sci Quantum as the founding engineer, and we found a limitation with the current tools, like the traditional tools like Cadence, Synopsys were too slow and very hard to use. So we basically wrote open source software that will allow us to make cheap, like faster and more efficient chips. Um, then I went to Google also for 5 years, and then we keep growing the community of users. So I think right now, yeah, we are reaching 4 million downloads. It's still three, I think. More than 100 developers. And today, yeah, if you compare GDS Factory, so GDS Factory open source is a very powerful layout generator. And we also made some open source device and circuit simulators that we can interface with. So, but now with GDS Factory Plus, we made a software that can do everything in one IDE. And the IDE will be based on VS Code. So today you will be using the IDE, and we'll be using this Cornerstone PDK, which is an open source university. It's a university PDK. This means that they made it at the university in the UK, and a lot of users can also contribute their designs. So this is also very important when you're doing PhD to make sure your designs don't get lost. It's important to put them in somewhere like Git. This could be in a private Git repository if you have some information that needs to be private. But a lot of times, if you put them public, it also helps you build like your portfolio of designs that you've done. We also support many PDKs under NDA, so this is also something that we also can help you with. But this one works a little bit different. You usually need to get them from the foundry. So this one that we're going to be using today, you will be using a shared user and a shared password to access the PDK and the sample project. So you will be using like VS Code, and you will have your schematic editor, your layout editor, your circuit simulator, your 3D viewer, all in the same VS Code. And the first part we're gonna do is gonna be like this hello world. So we're gonna do like hello UC Davis. So in here, instead of hello world, we'll write like UC Davis. And then we will be able to, the nice thing of GDS Factory is because we can describe your geometry in Python, you can do very powerful things. You can start with small building blocks like a square, and then you can do an array of squares, like 1,000 squares. Now you don't need to draw these things by hand. And the nice thing is that you can turn your code into a GDS file, which is what you send to the factory, but you can also turn your code, the same code, into like a simulation. And this is where you can make a very powerful loop where you try to get the results from the simulation to let the computer optimize. So this is the first part. It's a simple like hello world. The second part will be using the schematic editor. So we'll be doing a layout in the schematic. So this is the schematic. We will be doing something simpler than this. We'll be doing just a double ring filter, like one ring, another ring, and we will connect them with a route. And then you will put like a input port, and then you will put an output port, and that will show you the simulation of the rings. And then you can also change the length of the ring to change the resonance frequency of the ring, because the resonance frequency is determined by the cavity length. And the third part is the part that I always hated the most as a chip designer. It's gonna be checking errors. This is very important once you work with foundries, because foundries sometimes are very strict with the errors. So they don't want that you break their machines because their machine costs millions of dollars. So they need to check things like this. This is something that's too close. So that basically means that when you make this chip, the object will be merged. So this is something they don't want to happen. So they flag it as an error. And yeah, so for today workshop, you'll be going to this gdsfactory.com/workshop. I will do it on my computer so you guys can see exactly the process. The first part is gonna be waiting like for a minute. So I would recommend you get to this part of creating the cloud workspace as soon as possible. Um, I have shared a user and a password here, so that way it's easier for everybody to log in into the platform. Sometimes we also can do this progress. I can set it up here. I think we did last time in Calde, but we didn't use it, so we can use this one if you want. If that way we can know exactly where you are. So the first thing is like I haven't even to create a workspace, but the first thing is to create a cloud workspace. So I'm gonna use this user and this password. So I click in this link and I'm gonna use the user. Make sure you use the user and the password because that way we can all see each other and the password you can copy. If you also want, you can also break it into two screens because you're gonna be following this outline. So the first thing I'm gonna do is I'm gonna go to the cloud workspaces. I'm gonna create one with my name. I already created one just before the workshop to make sure everything worked correctly. So I call it new, but yeah, I had another one also 5 hours ago that I completely delete. But yeah, the nice thing is I can click, like, let me do it first and then you will see. The first thing I will do, I will put Joaquin Matres, my name, and then here I'm gonna create a template. So the template means that I'm gonna use a project based on a PDK. So for example, like Photonics Basic. So I'm gonna use Photonics Basic. No, I'm gonna use CSPDK, sorry, to create a workspace. And now what I'm gonna when this finished, it will be like this. So I'm gonna open the one in new. And the first thing you're gonna see is you're gonna see like open like a VS Code opens into your computer. It will also look kind of like this in this case. I have it here as open. This is running locally, but let me wait till this opens and you will see it. So I'm gonna see here. It will take some like a minute to start the server, but once the server starts, I can search for components, and I'm gonna be able to find something like hello. So if I click on the pencil, it will show me the code. And here I'm gonna change hello world by UCD, and I hit the I and then show GDS. So you can see as I change the UCD, I can change things like the size or any parameter from the layout. So the size could be 10 or it could be whatever I set up here. And yeah, this will be the first part. So once you finish the first part, you can go here and I was able to create a workspace and I'm able to find the milestone one, which is the hello world. Okay, so and I will leave like we have like 3 sections. So we will leave like 15 minutes for each section. That way we still have like a few minutes at the end for Q&A. So now I will let you be quiet and I'll let you do it. And if somebody has any question or gets stuck, you can share the screen or call for help.
Do you want people to move on to the second milestone if they're ready, or are we kind of waiting for everyone to be finished with the first one?
Perfect. Yeah, I was looking at the spreadsheet. It looks like everybody complete. Yeah, I think Dinesh almost there. I don't know, Dinesh, you need help. But yeah, we can. I think we can maybe continue. I can share the second part. So the second part is also described here. It will be, so we finished this first milestone. There's some extra bonus items at the end if you guys want to get a bit fancy. There's could be some bonus items where you can make it parametric. There's other things that you can also do. For example, I can show it here. You could add things like add information for testing, which is very important when you make chips, because the chips take a long time. Like if you want to test this thing at a particular voltage, you can add the voltage information there. And the nice thing of adding it there is that it doesn't get lost. If you rely on separate files, these files tend to get lost from the GDS itself. So one of the advantages of GDS Factory is that it allows you to put arbitrary data into the GDS itself. The other thing you could also do is add ports. Like when the chip comes back, if you don't know where the ports are, it's going to be very hard for the person who's testing the chips. And maybe it's not you. Maybe in a lot of companies, the people drawing the chips are not the same people as testing the chips. So you can add ports, and these ports allow you to see, okay, this is where my inputs and outputs need to be, and you can add information of where they are, so they're easy to find. But yeah, let me close everything. So the second part, we're gonna be creating a new. If you hit new, there you will see three things. So you can make a Python cell, you can make a schematic, or you can make a cross section. We're gonna make a schematic called rings 2. And for rings too, you have multiple options. You can search for rings. You can see here too, if I search for rings. So you can, we're gonna use this ring single. Like I'm gonna click on it first so you guys can see how it looks. This is a ring resonator. If I right click into the ring resonator, I can see the simulation of this. So I can see the resonances of the ring. So these resonances depend on the length of the ring. So as I can see here in this animation, so if I make the parameters of the ring different, like if you change the radius to something different, it will affect the layout and the simulation. So the longer the ring, the more resonances you're gonna see. So yeah, we will see that in the circle. So let me close everything, and we're gonna just drag and drop. You can drag and drop, or you can also hit the plus at the bottom here. And I'm gonna just use the default names. I'm just gonna put two rings. Like you could also use this button here to add, but I just drag it from the bar. So both options are okay. And before I connect the rings, I want to make sure they're at the right location. So I want to put like maybe ring 1, I'm gonna put it to the left. Yeah, you can click here, connect there. You can also zoom in, zoom out. You can move this one a little bit longer. Okay, you just need to click and then move. And now when the instance 2 is to the right of the instance 1, I'm going to use this automatic routing to define a route from one to another. The nice thing is that even if I move my ring, the routes will automatically follow. If I right click here, I can expose the unconnected ports, and I can right click. You can right click on the component, or you can right click on the port to expose it. So exposing the port adds the possibility of adding a simulation from input to output, as well as putting it to another circuit that we can do also in the advanced section. And once you hit the rocket simulate, you can simulate this component together with the layout parameters. And this simulation will include things from the layout, such as the propagation loss from the waveguides, the routes, the bends. If you wanna change some of the parameters of the layout, that you can, for example, let's change this, edit this ring to 11 microns. This will make this ring a little bit bigger. I don't know if you notice it grew by 1 micron in radius. And now if I simulate the component, the the spectrum will be different. So you get into a vernier effect when one of the rings has slightly different FSR than the other ring. So they only line up on one wavelength. And now that we have done these rings, if you want, there's another section, I think it's also in the advanced. So if you go to the section 2 in the photonics, if you have time, there's also an advanced section where you can turn it into a package. So this would be how to add it into an array and put it with paths. So if you want, I can also quickly do that for those of you who are a bit faster. But if not, it's okay. We can move. Um, we can also do other things. So like if I put rings 2 now, I can make an array of rings. So I can do 3 rows, and I can also put up a die with paths. There's different die frames that we could use, but I'm just gonna use die paths. And now, if I look at the layout, it's also nice to look at the layout before I start routing to make sure things are in the right place. It looks good. If you also want more space, you can also minimize this bar. You can also make a full window. Make sure you always have a big screen for layout, otherwise um, your eyes will get a bit strained. So you can see here, I'm connecting a route from this ring array into the output and automatically routes. Here I'm going to define 2 bundles. A bundle is a group of routes. So each bundle can have settings, such as the bend radius. Like I can make it 25, so you can see how the bend radius will increase. And the other setting I can have is what's the separation between these routes. And I can measure this by adding a ruler. So I can change this from 3 to 9. Let's say you use silicon nitride, you want to have something like larger gap. So yeah, you can configure all this. And I'm going to define another route. I'm going to call it L because it's going to go to the left. And I'm going to put these ones connected here. Yeah, so this will be the advanced section. You can still move the rings. So let's say you want to put your hello wall in the middle that we just did today. So you can always have some space there for other things like sample hello wall. Let's put it here. So you can the UC Davis. And you can also even put multiple if you want. The nice thing of this is that I added ports, so I could connect to it if I wanted. And I made it parametric, so I can put size. Let's say I want the UC Davis like in big, like a logo. It's very important to put the logo when you do research because that's how you get money. Like put some ads here, wherever space you have, and then take some nice SEM picture. Um, and yeah, this is the second part. I will leave you a few minutes, and if you have any questions.
Hi. I think I am stuck somewhere. I can't see the rings in my instances. Can I share my screen?
Yes, of course.
Thank you so much. Yeah.
Oh, yeah. Yeah, that probably happened. Let me see. This is like recursion depth, no? Like maximum. Yeah. Can you create a new one called rings 2?
Okay.
I think you're basically putting rings inside rings. I don't know if you see. Creates an infinite loop. Uh,
Okay.
yeah. Now it works. Yeah. Now click. Yeah, perfect. Yeah. Now you can. Yeah. Don't put it again. You're making another recursion.
Okay. Sorry.
It's okay. No worries. Just put a ring single there. Not put a. Don't put a one schematic inside himself because otherwise it creates an infinite loop.
Okay.
Yeah. This should maybe we should maybe try to catch this.
Mm,
Yeah. Just create another one called ring 3.
okay.
Create a new one. Go to
Okay.
new.
New.
Yeah. Ring
Okay.
3.
Mm-hmm.
3. Yeah. That one.
Okay.
And now you can click the plus at the bottom.
This one?
At the bottom
The
of the
bottom. Okay.
yeah there. Click there and then click again. And now search ring single. Yeah, the second one. The second one. The second one. Don't put
Yeah.
it again.
Okay.
And then add.
Ah.
Yeah, perfect.
Right.
And then
Thank you.
second one, you can click anywhere you want and then add.
Okay. Thank you so much.
Yeah. Now, if you hit the eye and then show GDS, now you can on the top right there's an eyeball, and the eyeball you can actually show the GDS.
Okay.
And yeah, perfect. Now they're a good position. You can move them if you want, but I think they're ready for routing. You can just route one to another. The routing is the one to the right of the one that you press. Yeah, that one. Then click there, and then you can connect the O2 of the first ring. So you need to click on the
Okay.
orange. Yeah, yeah, and then perfect. Yeah.
Yeah.
And then you need to expose the ports. So the other ports that are not used. So you can right click in the instance one and then expose and connect the ports. That one you can close for now. Right click,
I am.
expose
Oh,
and connect the ports. Yeah, it's the middle there. Yeah, perfect. Then and then the right one do the same. And, yeah, you can zoom out a little bit if you want to make sure the ports are. But yeah, I see the port in the right. You can zoom is with the mouse, so you can just scroll in and out. Or you can, yeah, or you can also use are you on the laptop? You can also
yeah.
hit there's next to the mouse, yeah, hit zoom to fit, yeah, like that, yeah, perfect.
Yes.
Yeah, now you can actually simulate. If you hit the rocket, you can simulate. There's a rocket
Mm.
at the top next to the eyeball,
Oh, yes.
yeah, and the simulate component.
Mm.
And then, yeah, you can go to the bottom and then click simulate. So now, right now, the rings are exactly the same. So when you look at the spectrum at the top, yeah, perfect. Yeah, yeah, zoom out. Yeah, you see them. They're exactly the same. So now you
Yeah.
can go back and then change one of the rings by right click edit and then change the
Okay.
ring radius.
Okay. I'll do that. Thank you so much.
Mhm.
Joaquin, someone in chat, it looks like they have a question just kind of about resonators in general.
Sure, yeah, go ahead. Well,
Sorry, yeah, I just had a quick question because my group, I've been working with with a particular ring resonator for a while, and I was just curious as to why, like when we simulate this, we see that the resonances have different powers, and for our ring resonator, we haven't really seen that. We're mostly just kind of pick whatever resonances seem to work for us, and we don't really think about what the power is at each resonance because this kind of tells me that there's some resonances that are better than others. And I was just curious if there's a particular reason why the power is different at different wavelengths.
yeah, basically different wavelengths you couple different amount. So you can always play, like if you wanna try to play with it, you can just add a few rings and then try to see how they behave. For example, like if you do, let's just try the ring single, just add a ring here. You could add if you couple a lot, like basically your quality the coupling depends on the gap and depends on the wavelength because larger wavelengths they come out more from the ring. So you get more coupling. And the other way to get more coupling is to reduce the gap. For example, like this is let me just draw this ring. Let me just do rings demo. Ring demo. So I can just drag a ring here. And you can just expose the unconnected ports and you can let me run a simulation of the default one. So when you see this ring, if you make the coupling like much smaller, like 0.1, you're gonna see simulate again. You see now the resonances are much
Oh, I
wider.
see.
So the coupling is too strong. So you're basically overcoupled. You can actually look at this in the phase too. Um, or yeah, the other thing you can do is that if you undercouple it, let's say you do a big gap, then simulate again. Now the resonance are gonna be very, very weak. You can see the peaks here. You don't get the 2 pi phase shift.
So it's essentially just a design choice, right?
It's a design choice. Yeah, it's also
Okay.
because the resonances, different resonances have different frequencies. Sometimes what happens is that the resonances, there's also backscatterings at the ring. So that backscattering either builds a counterclockwise mode that basically interferes with itself. So there's a lot of things happening in these kind of resonators.
Okay.
But yeah, you can spend a whole PhD studying these kind of structures. You can do pen circular, for example, if you want to have circular pens. So all these things you can customize it, and you can simulate it and see how it behaves. Now it is completely circular.
Oh, awesome. Thank you.
Perfect. Yeah.
Oh, someone in the room has a.
When we do simulation, can we only do passive simulation, or is it possible to put electrical kind of components to bias for inverter?
Can you repeat the question, Madeline? I could barely hear it.
I was asking when we do simulation, do we only do passive simulation, or is it possible to put electrical kind of bias and then try to do active simulation?
Oh, yeah, these ones are just passive rings, so you can only sweep the wavelength. But yeah, if you want to add, I mean, we have some tutorials online. So, like, let's say you do an active heater, and this is something that we could also show. Like, yeah, the PDK we're using only has heater, so the only active thing you could do there, you could add a heater on it. So if you go to the gdsfactory.com, there's a GDS Factory Plus, and then here we have videos on how to make like a active simulation, like a, for example, like a heater, like a finite element heater. And then you will need to do something like, for example, like GDS Factory itself. Um, we have the circuit simulator. You can run things like a phase shifter model where you apply a function of the voltage will change the refractive index, so you can do things like this.
And if we set up this GDS Factory class on our local machine, can we interface it with numerical?
Yeah, yeah, yeah. You can interface it with many tools. Like one of the nice things is that, for example, let's open it here. Yeah, so we have this simulation template. So this one is running locally, by the way, on my computer. So you have, let's say you want to download the numerical simulation, you can just download it and then you can run it locally. But you have to make sure you have numerical in that computer installed. The nice thing of this is that it avoids any mistakes because directly from the GDS Factory component, you turn it into a numerical simulation. And what we do for every PK that we have this layer stack, which defines the layer thicknesses and the material properties to make sure the refractive indices matches the one from the foundry. So yeah, you can play with this after the workshop. We have nice examples on how to do like a heater, this is an FEM heater. You can just run this and then it will simulate for different, as a function of the heat, how much refractive index you get. And this is how you build your model of your heater. So the first you need to draw the geometry. Okay, this is the heater with the waveguide. The heater is orange, the waveguide is like red. You can visualize it in 3D to make sure the geometry is what you want to fabricate. Zoom in and out. You can mesh it, and you can play with the mesh resolution depending on here I care about the waveguide here, silicon, and the heater is like tinitride. And then it also matters like the substrate. And then you can simulate for different currents, you simulate the mode with heat and without heat. And this will give you the phase shift as a function of current. So yeah, these are all simulations. And if I want to make it more efficient, like do you have any idea how I can make it more efficient? Like you have here my heater. It's a bit you have your waveguide is right here. It's very small. You have your heater here. It's very big. So a lot of the heat actually escapes. So a lot of people do either multiple waveguides to make the most of the heater, or you can also make the heater smaller. Like if you make this heater smaller, like that's remember this number. Like you get like 5 radians. So if I make the heater like instead of like 2, make it similar to the waveguide, point 0.4, 0.5. You'll get, let's see how much. Yeah, you get basically more than 4 times the heat, the phase shift You see here the weight and the heat. Yeah, we have a lot of for every component we have simulation templates. So yeah.
Joaquin, I have a few questions. What is the default thickness of this ring? And is it an insulator or is it just a vacuum?
Uh, Sorry, the feedback from the ring, like the
The thickness,
oh,
like
the
the
thickness.
dimension.
Yeah, yeah. This is coming from the foundry. So if I look at the ring, you can actually visualize it in three. So the thickness is 220 nanometer silicon. So this is
That's
coming from the
SOI
foundry
or
process. It's SOI. So this is yeah, it's just a
like
220.
the simulations assume that it's surrounded by air or insulator or half and half?
It's surrounded by oxide. So
Yeah.
the simulations, like I don't know, we have a simulation here, but I can take a look here.
It's buried in SIOX or SIOP.
Yeah, SSIOX. So you can run one of the, for example, like let me get a simulation template from like Tidy City, for example, has a one that you can see. So this one is taking the layout, and then we'll give you like a simulation where you can see the whole layer stack, including things like sidewall angle, which is also very important. Not only the materials, but also the angles. You see the materials. So you can see here in this, you see the core of the ring is this purple, it's a bit small. And then the cladding, and then you can plot the refractive index too. And the nice thing of this is that because you're defining it by code, so if today you're doing a ring coupler, but tomorrow you may do an MMI, automatically creates the MMI simulation.
Great. And what is this simulation running when we click there simulate? What is it running on?
Yeah, that's a very good question. So it's simulating circuit models. So we actually, you can turn it into a notebook if you want to see, like we can do something kind of like a quick and nice. Let's do like a gradient coupler layout where we're gonna do like a freeform layout. And then I'm gonna just show the GDS. So let's say you have a gradient coupler like this, and then if you want to run a simulation, because this component doesn't have a model, if you click now simulate, it will fail because there's no model. So like it will give you error. Hey, there's no model. So what I can do, I can right click and then add model. So we have a library of models, and these are basically S parameter models. The model itself is described in Python, and you can add things like the loss, the reflection of the fiber, reflection of the input of the grading, and then the bandwidth, which is the Gaussian bandwidth, the 3 dB bandwidth. And now I can actually right click simulate, and then I can simulate something that I draw from scratch. After attaching the model based on the simulation, it allows me to put it into like into a circle. So we can do something similar to what we did before, where we can put this gradient coupler into a ring. Let's put it into a single ring. And that's how you can go from like free form, like which is a lot of times in quantum, you need to define your own components and optimize them to have the best loss possible. But then in the end, you need to put them into a system and you need to be able to simulate them. So this is where like GDS Factory is very helpful. Like put together a layout, attach a model, like do some automatic routing. Then I can do like expose the ports. And this is gonna have reflection. So the nice thing is because I put some loss, like I can move things here like this, and then I simulate. The simulation is taking into account effects like the reflection. So this actually creates a fabric pearl cavity. Let me put more points so you can see the ripple. It's creating a fabric pearl cavity from this input grading to the output grading. So you can see this Gaussian response. has some ripple, which is what you usually see in the measurements. And the ripple periodicity is depending on the cavity length, like the distance from this point. So you go here and you go back, then you go here. So you build like a cavity
Yeah,
together with the resonator. So if I want to remove the cavity, I can make the ring. Let me close everything. Close everything so you can see easy with ring. Let me just look at the layout and I'm gonna make a smaller cavity. That way you can reduce the ripple. So now if I run it again, you will see the difference from a big cavity to a small cavity. I don't know if you notice now, the ripple is much smaller. And you still see the resonances from the ring, which is kind of nice. So yeah, this is like, if you want to also turn it into a notebook, like let's say you want to optimize this topology. I mean, this is just a ring with two green couplers, but you can actually generate this into a Jupyter notebook. And then if you turn it into Jupyter notebook, you can customize it as much as you want.
okay. And so if you want to add a new device or new element, you need to define its S matrix.
Yeah, correct. Yeah, like for example, like this GC, I just edit model, but if you want to do something like a hello world thing that we did, like I mean, I'm not sure you will add a model to this, but if you it's an S parameter, so I could just let's say this component has like it behaves like a 2 by 2, for example. It just gives you an S matrix. And you can actually click what's writing underneath is this sax. So it's a package that we wrote that returns S matrices.
Mhm.
So the
And
nice thing of this is that you have a lot of flexibility. Let's say you want to do an SOA model where you get the saturation from the SOA. You can put here very complicated equations.
so you can add the different response to different wavelengths as well. To
Correct.
either fix or
Yeah.
refract and just any other efficiency.
Yeah, like if you look at our couplers, these couplers will have also
Mhm.
the wavelength dependence, and this is coming from different wavelength as we mentioned before. As the wavelength is longer, it couples more because it just leaks out more. It's more uh, sticking out from the waveguide.
Yeah.
So the model is not having the page information, that's right.
Yes, I didn't hear that. The model is not what?
Not having the page information, just having the model. Like can you put a complex number for both?
Yeah, the model supports complex numbers. So the model is attached to the layout, and then it has some parameters too that you can pass. And when you do a simulation, you will see here the models are actually being loaded. So here you have a gradient coupler, you have a coupler, and you have the straights and the bends from the routing. So in the end, all this circuit is 4 building blocks, and each of them have an S parameter model.
Well, is it all right if you explain milestone 3 a little bit just before it ends? Because it's almost 3 o'clock.
Yeah, I mean, we have a recorded version of the workshop on the, if you go to gdsfactory.com/workshop, there's one workshop from University of Toronto. We have a lot of these workshops already being recorded. I think the best thing for this workshop is just try to play with try to touch everything that you can and see how much you can, how complex of a circle you can make, how to try new things and see how they behave. Like that's the best way to learn. Like if you wanna know how to make an efficient heater, you can just increase your thermal resistance by making the box bigger or undercutting the substrate. Um, the thing that the last part of the workshop is about DRC. I'm not sure if we'll have time to cover it today, but this is, as a photonics designer, is the part that I hate it the most, because once you think you are done with the chip, you basically still need to make sure the foundry accepts the chip. And this is where you've been working like months, late nights, and then you think you're done, then you're not really done. So it's important to run it beforehand and as much as you can. And this is what this button does. So you can do check and then check the DRC. DRC means design rule checking. So this is following the rules from the foundry. Yeah, so this was the last part. You guys can do it at your own time. We will leave the workspaces on for a few days. So you can see these errors. If some of you also feel adventurous and are not scared to touching somebody else code, you can go ahead and try to fix them yourself. So, but yeah, this is a bit tricky when you haven't written that code. But the errors, if you select them, you can actually highlight them. So you can also read what the error means. So this and closing, there's also a space error. You see there's something as too close. So the minimum space is 0.2, but if I measure here, I'm at 0.61. So you can change this min width or min space. Like if I change this from point to go to 0.3 or 0.5, whatever numbers you have. So now these are bigger than the minimum rule. So yeah, this is for you to experiment. And then there's width, minimum width. You can also make it bigger. And you can also remove some of these. Yeah, so you just play with it and then run it and then see how different um, different rules are being fixed. So make sure you also count them so to know if you're actually making it better or making it worse. But you see now I only have 5 errors left. So I fixed most of them already. There's still like a few left. So yeah, this is and if you also want to learn a bit more, we have a lot of videos on gdsfactory.com/workshop. And then gdsfactory.com, we have a GDS Factory Plus. There's a lot of videos here. Something I also recommend, because in the university I never learned how to use Git. Like in the company, it's very important to be able to work as part of a team. So there are videos here that start with how to do IT, how to install the library. Then with videos on how to manage a library, like be clean and organized and customize your components or your layers. Then there's tutorials about how to draw. Then verification is also very important. How to make sure what you draw, the foundry can fabricate, and how to you don't make any errors. And the last part is the simulations. But something is I think it's also very important. It's also not only the AI agent. This is basically how to use ChatGPT to make the chips. And there's Git for version control. So it's very important that everything you do, try to save it into Git. And this Git could be a private Git that you have at the university. But this is the only way for you guys to collaborate. Like please don't put these things into Google Drive, because what if one person deletes it? And you also want to track of the changes. So if you look at here, all the things that we've done today, they're actually stored here, and I can see if I make any change of any component. Like let's say somebody wanted to change the ring. Let me make sure, let's say I change the ring, and I make the gap like 0.3, 0.3. All this is actually gonna be stored in version control, so I can see any changes that I made can be stored and traced. So I could put them here, I could put them in the stage and then take a picture and then upload it. So yeah, I recommend watching this video too, even though it's at the end. And yeah, thank you for hosting today. And if you want to have a more advanced workshop in a few months, ping me and I'll be happy to jump.
Thank you so much for bringing us this workshop today. I think everyone had a good time and everyone learned a lot. So thank you everyone also for coming to this workshop. Thank you so much.
Let's give a round of applause.
Thank you. Bye. Thank you. Thank you. Bye bye.
Bye.
Bye.